Hello, my name is Nick-Marios Kokolakis, and the topic of my presentation is bounded rational unmanned aerial vehicle coordination for target tracking. This is joint work with Professor Kyriakos Vamvoudakis. First, we will start with the problem formulation. We consider that UAVs are tasked to pursue an evading target. All vehicles are modeled as dubious vehicles, flying at a constant altitude and at a constant airspeed. In fact, in a target tracking problem, we are interested in the relative motion between the UAV and the target. Therefore, by working in the polar coordinates, one can readily derive the tracking dynamics for each UAV. Finally, one can obtain the ensemble dynamics by defining the augmented state vector. In the sequel, we shall define the performance index. This guy allows distance coordination, whereas the player's input penalty functions are non-quadratic so that they enforce bounded input signals. Finally, note that the team of UAVs attempts to minimize J, while the target tries to maximize it. Depending on the cognitive capabilities of the agents, we shall consider two scenarios. The first one concerns a case wherein the agents are infinite rational, whereas the other has to do with bounded rational agents. First, we suppose that the agents are infinite rational, namely they know the existence of the game while sharing the same decision-making mechanism. Thus, in light of infinite rationality, the target tracking problem can be thought of as a zero-sum game. In particular, V star is a value function, while U star, D star is an equilibrium, namely the saddle point policies. Unlike the previous analysis, now we relax the assumption of the perfect rationality and we consider that the agents are bounded rational. Thus, we shall develop a level K thinking model wherein each player operates under the belief that all of her opponents perform K-1 thinking steps. Consequently, the level K UAV's policy comes from solving the following optimal control problem. The next theorem establishes that the policies converge to an equilibrium for higher levels as long as the following sufficient condition is satisfied. However, in our case, it is impossible to compute analytically the optimal policies together with the value function. Thus, we shall employ an adaptive learning-based framework. The critic neural network learns the value function, whereas the actor neural network learns the optimal strategies. Furthermore, a data-driven learning framework is introduced whereby the UAVs learn the target's level of intelligence. To validate the efficacy of the proposed approach, we carried out some simulations. This figure illustrates the target engagement. In particular, we observe that the pursuers circumnavigate the target while the target is evading them. Furthermore, while the pursuit is taking place, the UAVs are learning the profile of intelligence of the target. Thank you for your attention. And if you have any questions, then do not hesitate to reach out to me.